screen. Okay, today, instead of running all these problems in the terminal, the memory management stuff is usually easier to work through inside of Python Tutor, so you can visualize exactly what lines are creating copies and not creating copies, and where everything is, all the variables are referencing in memory. So we're going to go over the problems in Python Tutor today. Again, you should all be double checking to make sure that the problems that I have up here that I've typed in match the ones that are on your page, and I'm not making any typo mistakes that way. But this should be the first problem from the quiz. And this one is hopefully an easy one, that this is really the most basic concept right here, that when we execute line 2 right here, we create the list over here in our memory. And this XS variable is just a reference to this list, just a pointer to this list, just this arrow right here. But the list actually exists somewhere else in this object area of memory. And then when we do the ys equals xs, the assignment operator, the equals sign right here on line 3, does not make a copy of this list. It just has the xs and the ys variable pointing or referencing the same object over here, the exact same list. And so when I make a modification to the ys list, like appending a letter to it, it appends that to the ys list, but xs also references that same list. So when we print out the contents, both things will print out the same with the A tacked here on the end. Any questions about the first problem? Okay, number 2. Here, we're using all the other problems are somehow about reversing lists in Python. And in this problem, we're using the built-in reversing function, reversed, the past tense reversing function. And in general, anytime in Python we see something with a past tense like this, with a D on the end, then what's going to happen is it's going to make a copy of the container that you pass to it, and will do whatever the verb is here to that container and give you the, in this case, the reversed version of that container. But it's a totally separate container when you have the past tense version of the verb like that. And so the original list unmodified, the new list in reverse order. The alternative way of using built-in functions in Python to reverse a list is to do xs.reverse. And here it is not past tense. This is the imperative form of the verb, the command form of the verb. We're ordering xs to reverse itself right here. And when we do that, then it does not make a copy. It actually reverses the list in place. So the key thing to remember, you'll see this all the time in Python code, is that the past tense version makes a copy. The command version does not make a copy, but makes whatever change it is in place. Any questions on problem 2? Yes. Sure. Yep. So the question is, xs.reverse modifies the original xs container, and that is a true statement, yes. So in this case, I think the first time I ran it, I didn't even have a ys equals, so this line down here would have given me an error. Ys was never defined. Here we'll do the ys equals, and you can see that it's equal to none. That the imperative version of all of these verbs, all of these functions, returns none. The only modification, the only change, the only effect of that verb is in the original list itself, does not return anything, returns none. Good question. The actual version of this problem, though, was like this. And so that was the output. Any other questions on this problem? Very easy as we're going throughout the rest of the semester to get these two versions of all the functions confused. So yeah, just always, anytime you see like reversed or reverse or any function like this that could possibly end in ed, that's just a key thing to pay attention to and be aware of. Are we using the correct one, the one that we intend to use? In general, it is more Pythonic. So Pythonic means that it is what Python programmers like to do. It is more Pythonic to use these past tense versions of these functions like this, because they're less likely to cause unintended consequences down the line. And we'll see throughout the semester that they're not actually any slower than these ones down here. Sometimes you have to use these imperative versions of the functions, but whenever possible, it's more Pythonic, preferred in Python code, to use the past tense version like this that makes a copy. Problem number 3, now we're getting into the really interesting ones. Press next here. Again, when we define the function, it doesn't actually run the function. It doesn't evaluate it or execute it. Instead, it just creates this variable over here that has the same name as the function name. And that variable references the function object. And the function object doesn't really get displayed over here, but it's basically just all this source code inside the function definition. Line 6 over here, we create our first list. And then on line 7, we will actually call the reverse list function. So we go inside of it. Every time we call a function, again, we create this frame object down here that has new variables for us to work with. And in this case, this ys variable is going to be pointing to the exact same object as the xs variable, because xs is what was passed in for the ys value. Press next again, and here on line 2, we'll create a new version of xs right here. This xs is totally different than this one up here, because this one is inside of the reverse list frame. So this is a local variable, this is a global variable, and whenever we're inside this function, we always check local variables first and then global variables. Because there's an xs right here, every time we're accessing the xs object, it's this version right here that we're accessing and not this version up here. So let's go into our for loop right here, for I, y, and enumerate ys. Again, I is going to be the index that we're looking at, y is going to be the value that we're looking at. And each time over here to the xs list, which is the local list currently empty, we're going to be appending the y value that we get from enumerate. The enumerate function goes through the list in the same order, just like a normal for loop, so from left to right. So we're going to be appending to the list over here from left to right. And so here we have y currently equal to 1, because that's the leftmost entry over here in this list. And we'll append that onto this empty list right here when we execute line 4 right here. Press next, and you can see that that 1 was added over here. And keep going through like this, and it's just going to keep appending those entries over here in the same order. So it's not actually reversing the list, it's just creating a copy in sort of a roundabout way. And now returning this new copy of the list down here, putting it every time we return from a function, again, it will just replace the function call with whatever the return value was. So here our return value is this list. So our new ys variable will get set to this list down here. Press next. You can see now there's a ys variable right here that is pointing to this list, which was created inside the reverse list function. And print everything out, and everything is just xs and ys both exactly the same. Any questions about problem number 3? Number 4, another reverse list function. What's going on? Let's go into the function now. Most of the problem setup here is the same, but I was a little bit, I don't know, depending on your opinion, tricky or cruel about how I named the variables here. They're named differently in this problem than they were in the previous problem. Now, this xs variable right here is the parameter to the reverse list function. Again, this xs variable will mask the global xs variable. Anytime we're inside the reverse list function, we'll be referring to this xs variable right here. In this case, this these two variables happen to point to the exact same thing over here. And then when I do ys equals xs, now we have three different variables all pointing to this same object over here. We'll loop over the indexes now of this list, not over the values with the enumerate function. And starting with I, we got starting with I at the value of 0. When we run line 4 right here, we'll plug in 0 into this position right here. Do xs at 0 minus 1 is xs at -1. So the -1 position of xs is this very last position over here. And then we will assign that to the ys at 0 position. This is the ys at 0 position. So now when I press next, you can see that this value right here changed from a 1 previously to a 3 now. So I'll go back in time. So it's currently 1, 2, 3. When I execute this line for the first time right here, it'll change this value right there to a 3. Walking through this over and over again, we'll see that the value on the left and right of the equal sign every time from now on is going to be the same. So nothing is going to get changed anymore about this list. Then we return the ys list, which is also the same as the xs list, and print them both out. And they are both equal to 3, 2, 3. Any questions about problem number 4? Or anything about memory management? Yes. Number 18 on the packet. Let's see if I can open up the packet. And let's search for 18. This problem here? Okay, let's try to copy and paste this. See if that works. Into Python Tutor. And I need to indent. And hopefully that matches everything. Everything's indented too. Okay, so the question here is about problem 18. There's a lot of things going on inside of here, so let's take a look. Again, here we have the default value to our variables, to our parameters up here. So that's gonna, anytime you have the default parameters, always something confusing going on. The first thing to know about the default parameter up here is that this is going to create an object over here at the time that the actual function is defined. So the foo function over here, because it has this default parameter, we created this default object over here at the definition time. And this is always going to refer to this default object over here. Now in line 4, when we go inside the foo function like this, notice that as soon as I press next right here, a new variable right here, xs, was created on the frame, and this xs still pointing to this list out here. And then when I do this line right here, this is the I think the confusing line going from 2 to 3 like that. What's exactly going on between line 2 and 3? Here we have our xs variable. It is sitting to the left of an equal sign. And the very first time this happens inside of Python, this is creating this as its own new local variable. And so this no longer references this, this other object up here. This xs plus xs, the plus operation right here is going to take the two lists over here and over here and add them together. And so that's why we have these, this sort of double list down here, but it is an entirely new object, entirely separate from this one over here. And in general, the plus operator is always going to create you an entirely new object. So this XS is pointing at the new object created by this. When we return the length of XS like this, we'll be returning 2. And you'll notice in particular that this object up here, this original object, was never modified. None of the statements inside of here are statements that say modify an object. If I were to, I think the confusing thing is about this problem is, yeah, why didn't that object up here get modified? Because every time we walk through this, we'll see that it has the exact same results because this object, again, is never being modified. So it doesn't matter how many times we call this foo function down here, we always get the same results. If I did things that actually modified the object, I think the previous problem did something like that, x plus equals 1. This is like a modification of this object over here. And so that's actually modifying the object. The plus equal is modifying whatever the object is to the left-hand side. When we have the equal sign, though, it's never going to modify what that object is. It's just going to create a new object. If we had something like xs.append, that would also be modifying the object that exists inside of the foo function definition and not creating new objects down here. It's an extremely subtle point about how these default variables behave. And again, the main takeaway is that you should be like a little bit scared anytime you see things going on with default variables, that there's going to be some weird problems with memory management. I feel legitimately scared whenever I see something like this. This is like, okay, there's going to be some weird bugs going on, and I'm going to have to actually really sit down and think about this function when I see something like this. Did somewhere in that hit the things that you were wondering about, Pedro?
Yeah.
Olivia? Question is, go over the enumerate function. And the key thing about the enumerate function is we'll see exactly what it's doing under the hood later on in this course. But the key thing for us right now, if we have something like this is sort of the simplest possible enumerate function, that it creates over here, it loops over whatever the container is to the right. In this case, I put a string hello as the container. And the I value, the first leftmost value over here, is going to be the index into that container over here. And then the rightmost value will be the value that corresponds to that index. So the first index over here, h, is 0, and the x that corresponds to that is h. You can use any container that you want over here, whether it's a string or a list or a deck or a dictionary. Doesn't matter what container it is, enumerate works with them all, and it always returns the index and the value for you to loop over with at the same time. Any other questions? Yes. Yes. Let's see if I have it loaded up in my history. I will not load that. Here's the quiz. Here's the quiz problem. Let's copy the quiz problem to the clipboard. Paste it. Hopefully I'm getting my indentations correct here to match what the quiz problem was. Visualize that. And the question is, why are both the XS and the YS equal to 323 in this problem? And the answer is that XS and YS are never pointing to different objects. no matter which XS you're looking at here, they're both pointing to the same container over here, and YS is also pointing to the same container. So even though on line 4 right here, I'm modifying the YS container, that container that YS is pointing to is also the same exact thing as the XS container. So everything is going to have the same contents in it because it's literally the same container that we're looking at. Did that answer your question? Okay, go ahead and total up your points and somehow get the quizzes up to me. Any other quizzes that I don't have? Okay, today, so we'll have a real quick announcement, and then we're going to be talking more about search and recursion. So quick announcement is I posted on GitHub Issues a couple of research projects that I have going on over the summer. I think any one of these projects are things that you all could contribute to, and I'd be really excited to work with you all. So definitely encourage you to take a look at these and see if you're interested in them. The first two are related to somehow combining computer science stuff with like international relations. That I work with a lot of North Korean computer scientists, helping them improve various things about their internet infrastructure. And I have some projects that will help them out and help out communication between the US and North Korea. For the first one up here is talking about something called Unicode, which we'll be using in about maybe 5 weeks in this class. Unicode is the standard system for representing international text on computers, so text in any language. And for various historical reasons, it turns out that Unicode only effectively supports the computer usage in South Korea and not North Korea. But there are very low-hanging fruit here, things that with some knowledge of Git, people would be able to contribute to the Unicode code base and get North Korean languages better support. So that's one project. Another, archiving North Korean web pages. This is another project that we're going to be working on. I think it might be the very last or second to last project in this course about building a web scraper that is super efficient. Those of you who took CS40 with me built a web scraper that was very inefficient because things were not working in parallel. But we'll be building something in this class that is incredibly efficient, that can essentially browse all of the internet, like everything on the internet in just hours. And one of the uses that I have for things like that is monitoring how North Korean web pages work. And there's not a lot of automated activity doing that right now, but I would like to automate that more so that we have a better understanding of what goes on inside of North Korea. Last project down here, I'm sure many of you have heard about ChatGPT or used it to do various things. It's really an English-only system at this point. It has some sort of like accidental support for other languages, but I would like to give it more intentional support for other languages. And there's a sort of new style of training machine learning models that I want to explore that doesn't require a whole lot of machine learning understanding, but basically trying to take advantage of the fact that some machine learning models like ChatGPT already know English, and we already have good resources for teaching people who know English other languages. And so use those materials designed for humans and see if ChatGPT can learn from material designed for humans. If you have any questions about those projects, want to talk more about what they entail, happy to do that with you all in person 101. Some quick answers to emails that people have asked. I'm happy to try to explore ways of working outside the official summer research program of CMC to do something like this. But we'll have to talk about like in detail what that might look like one-on-one. Another common question that people have asked is this only for CMC students? And in the past, the SRP, the Summer Research Program, has been restricted to CMC students. I've asked them to extend it to non-CMC students this semester. They haven't made a formal decision about that yet. I think in like a week or two, there's going to be an announcement to the student body about exactly from your all's perspective what the program will look like. But again, I'm happy to try to work with students who are interested in these projects to find a way to get you to be able to work on them and get you the appropriate like academic credit and monetary compensation for doing that. So feel free to talk to me about any of those if you have questions. But today we're going to move on and we're going to be talking again about search and recursion, two very fundamental things in computer science. If there's like only one lecture to make sure that you understand from this semester, it's today's lecture, what we're going to talk about, because we're going to be talking about recursion in detail today. And your assignment this week is going to be based on recursion. Your quiz next week will be on recursion. And everything from here on out in the course will all be based on somehow on recursion and this problem of search. There's another note packet for today, a practice quiz. And there's a couple of little notes that I have up here. I'll just go over them real quick. This first note is that instead of having one quiz on this material, you will have two quizzes on the material. So help emphasize that this is an important topic, one that you will very, very much benefit from putting in good effort to study it and learn it and master it from the get-go. The first quiz will be worth 4 points, and the second quiz will be worth 8 points. So a lot of points dedicated to this topic. The material on this, the practice problems here, we're not going to go over them in class directly. They're for you to practice. These are all very abstract problems, thinking about recursion in the abstract. We're going to continue going over the notes.py file today that we started last time. I find that for most students, having a concrete example makes things a lot easier at first. But you really need to be able to work not just with concrete examples, but in like totally abstract settings. And so these are on totally abstract settings on this, what your quiz will be about. The last note down here is that there's something called a Stack Overflow, which we'll be going over later in class today. But there's some weird things like try and accept in these problems that are related to this Stack Overflow concept. Any questions about anything administrative before we get into technical material? Yes. Question is it to the same day? Yeah, not to the same day. It's the same normal quiz schedule. You'll just have your 4-point quiz next week, and then your 8-point quiz the following week. So if for whatever reason by next week you think you understand the material, but realize you don't when you take the quiz, you'll have another opportunity to demonstrate that you've mastered the material, and that second opportunity is worth more points. So it will overshadow, a good grade on the second quiz will overshadow a poor grade on the first quiz. Good question. Any other questions about administrative things? Yes. So the question is, what do I mean by abstract on the quiz? The notes.py has a clear application of solving the search problem. It's going to be intuitive why we're doing things. These are all basically just random lines of code that happen to use this recursion thing inside of it. And so there's like no meaning to what, it's just going to print out a number like 50 and you have to write out 50. But it's not like, why do we care what it's doing? There is no why do we care. It's just understand what it's doing. I don't know if that's a helpful answer, but that's the answer. All the quizzes, both quizzes will still have exactly 4 problems, still be the exact same format. Yes. The only printouts I have are whatever were on the podium over there. The practice quiz PDF is right here if you need an electronic copy or print out a second copy. Again, the main motivation for us to talk about recursion and this search problem is that for search, we talked about last time, there's this sequential search. And if you're using the right data structure, your runtime is going to be linear, this theta of in runtime. If you're using the wrong data structure, then you can get worse runtimes than this. But this is the best runtime you can get doing things correctly for sequential search. We're going to talk today, get to this thing called binary search, and your homework problem due next Tuesday is going to be based on binary search. And we'll see that, and also your lab this week on binary search, we'll see that the runtime goes from linear runtime down to this thing called logarithmic runtime, the log n runtime. And this is like extremely exceptionally fast, that this is basically instant. Anytime you see an algorithm that has a runtime like this, computer scientists just start celebrating because this is, you can do this as many times as you want, and there's no penalties for doing this. Everything that runs in the back end of Google or Facebook or Instagram, whatever web pages you're working with, they all use this logarithmic runtime so that they can access hundreds of millions of petabytes of data instantly. And so we'll be building up to being able to do that. That's our motivation. Now into the technical details. Last time, we started this notes.py packet talking about the sequential search with these iterative algorithms. Again, the ITR at the top stands for iterative. And we're going to go on to this sequential search recursive today and walk through it step by step, figure out exactly what it is doing. Again, the sequential search algorithm at the high level in the iterative version, we had a list that was being input, and we wanted to step through that list, walk through the contents one by one, checking whether each entry is equal to this value, y value that we're passing in. And if there is one value inside of here that's equal to the y value, then we get a true value as the result. So in this case, we have this list that contains the number 2 right here. So it gives us this 2. And down here, we have a list that does not contain the number 6 anywhere, does not contain the number 6 anywhere, so it gives us the false. And in our previous solutions, we were using for loops for implementing this. Again, for loops, think iteration, for loops. They're like synonyms for each other. Sequential, iteration, for loops. Recursion down here, we're going to see that this problem is going to, or this function is going to solve the same problem, just in a different way, in a recursive way. And in this case, the recursion is not going to be particularly helpful, but when we go on to the next page of these notes, getting to the binary search, then the recursion will be extremely helpful for us. Last time, again, we said that there were 3 rules for recursion. We didn't exactly get into what they mean or why we have them, but we talked about there must be a base case for the recursion, and a base case is a return statement that does not call your function. So a just ordinary return statement. These are base cases for our recursive function. You must also have what is called the recursive call to the function. So we're down here on line 14. We have sequential search REC. This function is calling itself inside of itself. That's what makes it recursive. And then somehow the problem must be getting smaller each time we do this. And over here, we're doing a slice to make the problem smaller each time. I'm going to switch over to Python Tutor to walk through this in detail. I recommend still having these notes out in front of you, and I'm not going to be like writing things down ever, so there's nothing specific to copy, but try to write down whatever things about Python Tutor are the things that are going to help you on future quizzes understand what's going on in recursion. Okay. Here is our sequential search REC function, copied exactly the same as it is from the notes. But down here on this last line, I'm calling this first test case right here. I'm going to visualize this execution. And before we step through this, are there any questions about the setup of what's going on? Is everybody, again, this is like the next 20 minutes are the most important 20 minutes to pay attention to, both in terms of like what we're talking about, but also so that you can go through yourself in the future through these Python Tutor on these same problems and make sure that you're paying attention to the right things. So again, I'm doing sequential search recursive, calling the recursive function on the first test case. And let's go ahead and press next and start walking through this and see what's going to happen. So at this point, I've just entered my function down here. And again, every time I enter a function, we create this frame object, this frame over here on the left-hand side of the window. The frame is always at the top, shows what is the name of the function that we're currently inside of, and then what are the variables that we have access to inside of this frame. On line 16 down here, when I first ran this function like this, then I passed in two parameters to the function, this xs and this y parameter. Xs, again, is this list right here, corresponding to everything in yellow, and the y is the number that I'm searching for, the number 2. And then walk through it. I'll walk through these 4 if statements right here. None of these are going to evaluate to true. The length of xs is not equal to 0. The value at the very 0 position of xs is not equal to 2, the thing that we're searching for. So both of these two things here evaluate to false. We do not do them. We go on to line 14 right here. And this is the weird part. So this is the part to make sure to understand what's going on. On line 14, I'm going to call the sequential search recursive function from inside of the sequential search recursive function. And again, every time you call a function in Python, no matter what the function is, you always create a new frame over here on the right-hand side, a new one of these blue boxes. So as soon as I press next over here, you can see there's another sequential search recursive frame created down here. This one is on the bottom, which means this is the one that we're currently inside of, currently looking at. Press previous to go back again. This is before we ran this line. Now press next to run that line, and it creates this frame down here. The important thing to keep track of about this frame are the values of these two variables down here. Notice, first of all, that the names of these variables, xs and y, match exactly the names of the variables in the previous frame that we were inside of. That's okay, though, because these are local variables inside of Python. So now, whenever we're inside of this sequential search recursive function right here, we always look at the local value, the local variables for the particular frame that we're in. So when I come down here on, say, line 10 right here, execute this, how do I know which xs value I'm looking at? I'm always looking at the one that's in the current frame that I'm currently in, which will be the frame that is on the bottom of this set of frames over here. The xs over here, you'll notice, is different than the xs up here. It's both pointing to an entirely different list that up here we have one list. Down here, it's a totally separate object down here. So it's an entirely different list that we're pointing to. the contents of the list are also different. The reason the contents of the list are different is because right here, I'm taking a slice, removing the very first entry of this list. And when I do that, I removed this 1 right here, only kept everything from index 1 on. So 35420 matches 35420 up here, the 1: matching all of this. Every time I do this, so we'll walk through this again, you'll notice that once again, I hit line 14 down here. Once again, I call my sequential search recursive function down here with the 1: slice over here. And so every time I get to this line, the list over here is shrinking in size. The list over here is shrinking in size each time because I have this slice over here in my recursive call to this function. This is one of the key important things that you need to make sure that recursive functions always do, is whatever the container it is that you're operating on, the container must always be shrinking in size. That way, the container will eventually get to size 0, and you can stop at size 0. Here, this if statement right here will check to see if it ever gets to size 0, and it will cause us to stop when we get to size 0. Let's keep going on. So again, each time I do this recursive call, we're adding a new frame down here. And this first if statement right here is checking to see if our list over here is totally equal to 0, then we'll return false. This statement 12 right here is checking not if our length is equal to 0, but if the current front of the list, the current front value, if that is equal to y, the thing that we're looking for, then it will return true. So this is the situation where the list does contain what we're looking for. In this case, we're looking for the number 2. And eventually, there's a 2 over here. Every time we make this list smaller, that 2 moves closer and closer to the front. So eventually, it will be in the front. Not yet, but now it's in the front. And so now at this point, this did not evaluate to true, but this line right here will evaluate to true. And we'll go inside of line 13. I go inside of line 13 right here. And when I do that, now it says return true right here. So scroll down just a little bit so we can see how the return value is going to affect this frame. I'll press next. And you can see that it says return value of true. Again, anytime in a function we have a return value, we go back to where that function was called, and we just copy and paste that return value for that function. So here, the return value of this function call right here is going to be true. So as soon as I press next, we're going to remove this frame and go back to this frame, back to this line right here where we're calling this frame with these values right here, but we'll replace that line with the line true, or with the value true. So we replace this thing with true. Now we know that the return value of this frame is going to be true. The return value of this frame is going to be true. Return value of this frame is going to be true, and so on all the way back up until we get that this whole thing right here evaluated to true. Lots of things going on here. Very easy to get confused at various points. But the key things, I'm going to go over the key things again. What's going to be the 3 laws of recursion over here that the textbook calls these the 3 laws of recursion. I'll once again say how these relate to the Python tutor code that we're looking at. The first thing over here is what makes something recursive is this line right here does not make it recursive. This is just an ordinary function call. And this function call happens outside of the function up here. So this line up here has nothing to do with recursion. What makes it recursive is this line right here where we're calling the function inside of the other function. So that's the first thing that you need for recursion is the recursive function call right here. Without that, your function is not recursive. It is an iterative or a sequential function. If we only have this line right here, though, then we're never going to stop our, we're always going to keep calling ourselves over and over again. And so we need some situation that's going to tell us to stop, some situation where we do not have the recursive function call, some situation where we have a return followed directly by a value and not by the recursive function call. And that is our base case. Every recursive function must have a base case. Again, the base case is where you are not calling the recursive function. And then the last thing that every recursive function must have is that in your recursive function call over here, the problem size must be getting smaller somehow. So here it's getting smaller because I'm using this list slice over here. I want us to see what's going to happen if we remove the base case over here. So we're going to break all three of these laws of recursion one at a time, and we'll see what are the bad things that are going to happen. The first thing that we're going to break is we're going to remove the base case like this. And now we'll see what happens. I'll visualize this execution. And if I step through, we'll see that the problem is in fact getting smaller over here on the right-hand side. Eventually, the problem size will get to 0. But the function is going to keep calling itself with an empty list. If we have an empty list that we pass in up here and we take a slice of an empty list, we're still going to get an empty list as the result of this slice. So we're still going to keep calling ourselves over and over with an empty list. This function has no indication of when it's ever going to stop. And so this is an infinite recursion. This global frame area, this frames area over here, this area is sometimes called the stack because you'll notice as we call a function, we are putting something on the top of it. And then after we're done calling it, we take something off the top. So it's like pushing and popping onto the stack. So this area is often called a stack. And if our recursive function has no base case, so it goes on forever, then we are going to keep pushing things onto the stack forever. And we get what's called a stack overflow when the stack is too large. We get a stack overflow if our recursive function has no base case. That is the source of the name of the Stack Overflow website because it's a very common error message to get. And yeah, so that's why they called it that. Here, on Python Tutor, they don't give you the full error message. They just tell you that they stopped since the stack has 30 functions on it. That's the maximum size of the stack on Python Tutor, and they tell you that your code may have infinite recursion inside of it. I'm going to switch over to Python just for a second, just so we can. Yeah, I will switch over to Python. I don't have the terminal open, so I'll just do that really quick. Log into, if I can type, log into the Lambda server. There we go. And we're in the topic for recursion. Again, this is the notes.py file that we're looking at right here. Make this a little bit bigger. And we were looking at this sequential search recursive function. This is the same function that we have in Python Tutor. And again, if I run the doc tests, Python m3-m doc test on notes.py, everything's going to pass. But if I modify this so that the sequential search recursive function does not have these base cases down here, I just want us to see what are the error messages going to look like. So if I modify it like that, this is the same way that I modified it in Python Tutor. I just took out the base cases. I want us to see what the error messages are going to look like here and rerun the doc tests. Then you get this this recursion error down here telling you that the maximum recursion depth is exceeded. So if you get something that looks like this telling you that the maximum recursion depth has been exceeded, that means that you probably have a recursive function and forgot the base case somehow. The other, so that's the first rule of recursion, that you must have a base case. The next rule of recursion was that the problem size needs to get smaller and smaller each time. let's add this back in. So it was if length of XS equals to 0, return false. And if XS of 0 equals Y, return true. So this is the working code. This is the code that's doing exactly what it's supposed to do because we have the base case, we have the recursive call, and our code is getting smaller each time. If we run through it, then we won't get any error messages down here. If I open this up again, but I change it so that the problem is not getting smaller each time, but staying the same each time. So I delete the slice over here. Then now every time I make my recursive call, sequential search recursive, the size of the container over here, XS, is staying the same on each recursive call. We're never modifying this XS container. And so if I visualize that and walk through, then we'll see that it is in fact doing all of these things, but the XS variable over here is always going to be pointing to this same exact container over here. We're never making a new one that's smaller. And so every time I run through this problem, it's going to give me the exact same results. Press last to jump to the end. And in this case as well, we will get that same Stack Overflow message, this warning right here that you might have infinite recursion. So those are the two key things that you need. You must be modifying your problem somehow so that it gets smaller in some way. You can never be using the exact same parameters here as you used up here. You must change them somehow. And you must have a base case over here that's going to stop your problem once it's gotten to the smallest problem possible, or once it's gotten to the correct situation that you're looking for. The last thing about the recursive problem that you need is the call to do recursion. So I'm going to delete this last line right here, delete the recursive call right here, and we'll see what happens. If I visualize that execution and try to step through it, we'll just see that we instantly are done with this function, and we never consider all the possible values. So again, we need that recursive call down here, return sequential search recursive. XS must make the problem smaller, and in this case, passing in the same Y. And now we're once again back to the correct implementation of the sequential search recursive. This is doing the exact same thing as our iterative algorithm was doing, that it's still going over each one of these entries one by one, checking to see if it's equal to the 2 value. It's just coded up in a weirder way, less obvious way. In general, it's sort of if you go on to take theoretical computer science courses, one of the theorems that you will discuss is that anything that you can do with iteration, anything you can do with for loops and while loops, you can also do that with recursion, and vice versa. Anything you can do with recursion, you can also do with for loops and while loops. But what we're going to see is that recursion is going to be much easier to actually reason about and prove things about your programs. At this point, it's a little bit harder. But once you sort of get familiar with it, it'll be easier. You'll be able to just look at something and instantly know that it's a login runtime or whatever the runtime happens to be. Whereas with iteration, that's not always possible. If you're able to use a for loop with an iterative algorithm, then for loops are the easiest thing possible. But if you can't use a for loop, if you're thinking that you might have to use a while loop to do something, then recursion is going to be the thing that will be easier to use than while loops. That's a lot of things that I've said at this point, but this is a good time to stop, come up for breath, see if there's any questions that people have. Yes. Yeah, so the question is here, with this problem that I have right here, this example, we have the 2 over here. And so it's going to hit the 2 before it has sort of shrunk the problem to its smallest size. If we keep running through it, we can see at this point now 2 is the very front of the list over here. And at this point, this will evaluate to true. This condition right here evaluates to true. And so this, we will go inside one of these base cases right here and hit the return true. Because I'm doing return right here, it means that the control flow, the flow of execution of this code, will never get to line 14 inside of this stack frame right here. In this stack frame right here, we're going to execute line 13 instead of line 13. This return means that this stack frame immediately goes away, and whatever we're over here, whatever value we have over here, will get passed up to the previous stack frame. So right here, when I press next, we get the true value right here as our return value in our sequential search recursive, get true right here. We will not call this value down here. We will not call line 14 in this stack frame, and so we will never get a smaller list than this. We will never get the list that contains only the number 0. As soon as I press next right here, we're going to go back to this stack frame, and so I press next. You can see we're back on this stack frame. Line 14 on this stack frame is what we were previously executing, so this whole thing gets the return value from our previous stack frame. Line 14 in this stack frame right here gets the return value from this stack frame here as true. And so now it substitutes true right there and tries to return true. We get return true again, and the return true is just going to keep getting passed up through all of these stack frames until at the very beginning, this whole thing will evaluate to true. Did that answer your question? If this is seeming weird and hard and like not 100% making sense, then you are an ordinary human. That's the ordinary process that vast majority of people go through when first working through recursion. And the quiz notes are designed to sort of work you up from the smallest, simplest recursive problems to more complicated, interesting ones. And really strongly recommend you spend a lot of time with the practice problems for this coming quiz. That'll really help cement these recursive problems. Yes. Yeah, the final results here, the sequential search recursive function gives us the exact same results as the sequential search iterative function, just the internals of how it's doing it are different. So the question is, what is the runtime of this? At this point, we don't have the tools yet to talk about the runtime. Next week, we'll go over the runtimes of this. On lab this week, you'll do all these different versions of the functions in notes.py, run them all and empirically measure their runtimes. And then we'll go over the mathematical formulas next week. Come back over here to the notes.py file. There's a couple of other recursive functions that we're not going to go over in class here for the sequential search recursive. But the key idea is that they just have, again, slightly different implementation details of having helper functions that are defined internally that do the work. And you'll see that these 3 different versions of the functions will have different runtimes empirically when you evaluate them. And then next week, we'll talk about why exactly they have those different runtimes. What we're going to do for the last 10 minutes here of the course is the lecture today, we're going to talk about binary search. And again, binary search, this is the most fundamental, most important algorithm in computer science. This is the every time you're, again, connecting to Google, Facebook, any web page, they're sorting through all of this data. How do they get it back to you so quickly? It's because they're using binary search to do it. And we're going to get an intuitive feel today about why binary search might be fast. But we're not going to, next week, we'll talk more formally about why binary search is fast. Here, this first version of binary search uses an iterative algorithm. Again, if we come down to line 20 down here, we can see there's a while loop. While loops mean iteration. But while loops should be terrifying to you. They are terrifying to me because while loops mean things could be infinite. Infinite loops could happen. That's awful. Things could be, they're also really hard to understand, hard to figure out what's going on, hard to determine what the runtime is of them. We're not going to work through the binary search iterative version right here. I just have it just so that you can see that it's possible to do it in an iterative version. And instead, we're going to work through the recursive versions. I have two recursive versions for us, a longer one up front, and then the very last one down here, binary search recursive 2 is shorter. That's the one we're going to start with. I'm going to come back over to Python Tutor. And here we go. This is the binary search REC2 function that we're going to take a look at. Again, this is implementing the exact same thing as the iterative function. We're going to walk through exactly what it's doing here, why it's working the way it is, and get an understanding of binary search from that. The key difference between binary search and sequential search is that what the prerequisites for the function are. In binary search, we have to assume that the XS container up here is already sorted for us from lowest to highest, whereas in sequential search, we did not make any assumptions about the ordering. So if you look at the containers down here, 1, 3, 5, 7, 9, 11, it's sorted order. If you look at the examples in sequential search, non-sorted order. And binary search is going to take advantage of the fact that things are sorted in order to make our problem faster. Let's visualize this execution, and we'll step through what exactly is going on here in binary search. Line 13 right here, I'm just going to call the function with the first test case, and we'll go inside the function. Here is my list, 1 up to 11 by 2, all the odd numbers. We're looking for number 9. And again, I have a base case up here. If the length is equal to 0, then we'll return false. So we're not at that base case. We'll come down here to this variable right here, line 5. What line 5 is doing, mid is the midpoint or the middle index of this list up here. You can see, so first index is 0, last index is 5, 3 is sort of like the middle. This the / formula over here will make sure that we get an integer as the result and not like 3.5. And yeah, so we're not getting the exact middle of the list here, but we're getting pretty close to the middle. And then what we're trying to do is we're trying to find our y value, the thing that we're looking for, this 9 value right here. Is it greater than or less than the index of the middle? In this case, we have a 7 right here. Where our middle value, again, is 3. Our middle index is 3. The corresponding value is 7. And so XS at mid, this right here, is going to evaluate to 7. That is not greater than y, so we're not going to go into this recursive call right here. Instead, when we get XS at mid is less than y, 7 is less than 9, so we will go in and do this recursive call right here. And what's key about this recursive call is that when you look at the smaller problem that we have right here, the smaller problem is a lot smaller of a problem. It is a much smaller problem that we're going, not just discarding one value at a time, but we're going to discard all 3 of these values. We're starting at the midpoint plus 1 and then going to the end. So here was our midpoint right here, start at plus 1 and go to the end. Press next, and you can see that our new list down here is much, much smaller than our old list was up here. So that's the key thing about binary search. Different than iterative search is that different than sequential search. At each recursive call here, my list is not getting just a little bit smaller, but it's getting a lot smaller. It's shrinking by half, or even more in this case. And now our value 9 is still in this new list. I just have to find where exactly in this list is it. Press next. Our list is not equal to 0. Press next again. Find the midpoint. In this case, our midpoint's going to evaluate to 1 right here. Our XS at mid, that is 11. That is greater than the y value this time. 11 is greater than the y value. And so when I go through, I'm going to use this binary search recursive call right here. We're going to look at the things to the left of the midpoint this time instead of the things to the right of the midpoint. And now that's going to leave us only with the 9 value. And if I walk through, it's going to come down to this if statement right here, this last base case, and return true. And so there was only 3 sort of recursive calls here, 3 lists created, whereas if we were using the sequential search version that we had before, we'd have to go through each one of these things in turn. I'm going to modify this code a little bit. We're close to the end of class. I want to make sure that we can see this one last example here before class ends, and then I'll take questions after class. So I'm going to modify this example here by first just changing this list value right here, list of range of 1, 11, 2. This is going to give me the same exact list that I had before. It's just in a little bit more formulaic way so that it'll be easier to, so I guess I should go up to 13, I think. It's just in a little bit more formulaic way, so it'll be easier for me to modify this list and generate a new larger list. But everything else about this problem like this is the same as what it was before. And what I'm going to do is instead of going up to 13 here, let's try going up to, say, 100. So now we have a pretty big list that we're trying to go through. You can see that it's created this giant list over here, and I have to scroll quite a ways in order to get to the end of that list. So it's a pretty big list. If we were to look at all those entries, it would take us quite a while to go through things. But the way this is working here, every time I hit this if statement right here, we calculate the midpoint. Here, the midpoint is 25 because there's 50 elements in this list. And I'm only going to consider the things to the left of 25. So I press next right here. And we can see that this new list down here is much, much, much smaller than the previous list. Much, much, much smaller than the previous list. Walk through it again. Again, we cut the list down in half, making it much smaller. Walk through it again. And now the list is really small, back to what it was in our first problem, going from 1 up to 11. And keep walking through. Eventually, we're just down to this 9 all by itself. So now it only took us 6 iterations here, 6 loops through or 6 recursive calls in order to analyze a list that had 100 different elements in it. And I can make, no matter how big I make this list, it'll be very, very efficient and walk through it efficiently because we're not removing one thing at a time, but we're removing half of the things at a time. That's the key thing again for binary search. We're removing a lot of things at once. This is going to be where we'll stop for today. I'll take any questions that people have after class right now, or we'll have the whole lab period on Friday to talk about this thing. And your lab problems, again, are going to help reinforce for you the difference between binary search here and the sequential search.